Part 2 of today's session is DC circuit theorems. So what we're going to do, and some of this we've had a bit of a look at on the science pressure. We're going to look at ideal voltage and current sources, and I believe we did do that bit on science. We're going to represent real voltages and current sources, and then we're going to look at how that theory is used in what's called the superposition theorem, which will allow you to calculate the circuit parameters in a circuit with more than one source. So more than one voltage source, more than one current source. Okay, and then we're going to look at how we can use that to solve the problems. So I think you've probably seen this before. An ideal voltage source would be one that, regardless of the load we put on it, regardless of the load current IL, we'd always get 10 volts at the terminals. We'd always see 10 volts there if that voltage source was ideal. It would mean that the ideal voltage source has no internal impedance, no internal resistance, the impedance in the AC circuit. Right? This would mean that the voltage across the load is equal to the voltage across the source for any value of load resistor, regardless. Alright, now that situation is in terms of a real voltage source. So, how do we represent a real voltage source? We do that by having an ideal voltage source series that's internal resistance. Call that RS, representing the internal resistance of the source. So this circuit we've got here could be inside this green dash line, a battery or a DC generator or something similar. And these are two output terminals. But when they're open circuit like that, no current is flowing, you put a voltmeter across there, you would measure VS because there's no current flowing. So when the circuit is open, terminal voltage will be S. However, if we connect a load so that current flows in the circuit, we would then drop some voltage across here. For instance, let's say Vs was 2 volts. Current, we drop 1 volt across there. We then only see 9 volts at the terminals. And the more current we drew, the more we drop across the RS, for the more the output current of that source would be. So that's what we call loading effect. As we draw more current, actually loading that source more, and therefore the terminal voltage will drop. Like your car, if you put the headlights on and try and then start the engine, what happened to the headlights? They go dim or go off, and that's because the high current you're drawing the starter motor, effectively drawing the terminal battery down. Right? So, if the open circuit voltage battery is 12 volts and its internal resistance is 0.5 ohms, find the terminal voltage of the battery when currents of 2 amps, 10 amps, and 20 amps are drawn. So it has subload with a current flowing in that direction, How are we going to calculate the terminal voltage of the battery when we draw 2 amps? how are we going to calculate amps? We want to know. I'll do it in green, and we'll keep the. This is when the current's 2 amps. VL is it not VS minus the voltage across the internal resistance by Kirchhoff's voltage law? That voltage, the voltage here, is going to be that voltage. Those two voltages add up to that. Yeah, so by Kirchhoff's voltage law, the voltage at the terminals is the source voltage. Take away the volt drop across that resistor. How can I calculate the volt drop across that resistor? Someone said Ohm's law. I times Rs. So if I put that in here, it's Vs minus I times Rs. You can then do the calculation in one go. 12 minus 2 amps, wasn't it? 2 times 0.5 equals 11 volts. So with half an amp flowing, we'd get 11 volts at the terminals. If we have, I'm going to do the calculations for this in blue, if we have 10 amps flowing, VL is equal to 12 minus 10 times 0.5 is 7 volts. Yeah. And then lastly, in red, we have 20 amps flow. VL 12 minus 20 0.5. I think I'll find that's 2 volts. So as you can tell, current, the effect gets worse and worse, and the battery becomes less. Okay, and you could think of a battery becoming discharged in a way as an AA cell, for instance, discharge. You could think about a model in a simple way by imagining that as it discharges, its internal resistance is getting bigger, so the terminal voltage is dropping, and eventually it drops to a point where it won't operate your iPod anymore or your phone. Yep. Okay. I didn't know whether I'd ever come to the day when the term iPod was old-fashioned. I've still got my old iPod Classic. They still sell for more or less what they thought for on new. Okay, so are you all okay with that, yeah? Right, ideal current. Most thing to remember the ideal voltage source is that its internal resistance, ideal voltage source, internal resistance is 0. Yep, must remember that. Okay. Ideal current source. That symbol there, and I have to tell you, I've noticed on Q quite universal simulator, QCS, they use a slightly different symbol for current source, but that's one I've always done, and that's from a textbook I use. Two circles interlinked as a current source. All right. So if I had a current source, an ideal one of 2 amps, it would always deliver 2 amps, regardless of the load I put on and what the terminal voltage was. Okay. An ideal current source has an infinite internal resistance, so there's no current loss within the source at all. Alright, so the so-called perfect current source would always deliver the same current and have its terminal voltage Vt determined by the load resistor RL. Again, in real life, that isn't achievable. Can't get an ideal current source. You can get a controllable current source that will do that within certain parameters up to a certain maximum, controlled electronically, but a trace current source cannot get ideal and can't get ideal voltage source either. So how do we represent a real current source? We represent it by having an ideal current source like so, in parallel with its internal resistance. So this bit terminal is a representation of a real current source. And so we're representing the lost current path through RS. Yep. So whatever you put on the end, you'll lose some current through here that's not there, because there's a parallel path. So when the terminals are open circuit, the current I passes through the internal resistance, you lose all of it. Okay. One thing that you should be noted is that this is a representation of a current source would behave under. Sometimes it's useful for a certain current source. So just whether you consider it as a current source or voltage. Okay? And everyone happy with that? Happy with that. So, example, ideal current source of 4 amps. Internal resistance 60 ohms. And find terminal voltage where the load resistance is 20 ohms, 150 ohms. Do that. Going to find Vt. Will that work? Is all that that's flowing here, but some of that goes that way and there. Yep. You to do that. We want to find I think I've asked for it. But we have to write it on that current pass passes through that parallel combination, doesn't it? So if we parallel up them two distances, then do Ohm's law and parallel equivalent, we'll find the voltage, then we'll find the voltage, find the current through the load and the current through the load. So we can say R is, how do we calculate that? RS times RM over RS plus R 60 and 20. Therefore, VT times RP plus 4 amps times the 50 ohms. Therefore, higher is equal to V terminal over 60 ohms, wasn't it? 20 ohms, sorry. 60, 20 equals 3 amps. Therefore, I IRS equals 4 amps plus 3 amps equals. So under 20 ohms, we're losing 1 amp for the internal 60 ohm and 3 through the load. Yeah. Now do the same calculation for load 150 ohms and see what happens. Right, what we got then? RT $210 then, yeah, equals ohms. VT then is SS 4 times we got 171.4 volts IL 171.4 over 150. I got 1.14 there. Current amps, and IS is 4 minus 1.14, 2.86. There or thereabouts. Yep. They add up to 4, don't they? Okay. So with the 150 ohm load, we're only getting 1.14 amps through the load and losing 2.6 amps internally in the current source. All right. So All after that, we'll move on. Network theorems. There are a number of theorems that electrical engineers can use to analyse networks and determine the superposition theorem we're going to look at now. Thevenin's theorem we touched on in science, we'll do that next session. Norton's theorem is a similar thing to Thevenin's theorem, except that ends up with a current source instead of a voltage source. And the maximum power transfer theorem is something around you can use around the two Thevenin's and Norton's theorem. I'll explain more about that when we get. We're going to revisit it. Can't be doing anything that different, Dom. We've pretty much covered it, and that, but we might eventually go on to a few basic circuits. So, superposition theorem states that in a network containing more than one source, we're only going to do two because it's principle and to have three sources, four sources. It's not, you're not going to learn anymore, but you're just going to do a lot more work. Okay? So I ever give you two sources. Well, you're not more learning. You're just, as you'll see, just mean repeating the calculation you're going to do one more time. You haven't learned any more by doing. No, you're better off practicing another question with two sources than you are doing a question with three sources in it. Trust me, Dom. Right? Okay. You'll see in a minute why I wouldn't teach you anything more. All right? Believe me. Right? Listen. Okay. In any network containing more than one source, the current in, or the potential difference across any branch in the network, can be found by considering each source separately and adding their effects. So you consider the effect of source 1 separately, calculate the currents, voltages, whatever you're interested in terms of that version of the circuit. You consider source 2 separately, you bring them both together, and you combine those currents and voltages into the overall currents and voltages. So when you consider the distribution of one source, all other sources in the network are replaced by a resistance equal to that ideal internal resistance. Remember I told you to make sure you remembered that an ideal voltage source has got zero internal impedance. So we replace a voltage source circuit. If you're replacing the current source, the ideal impedance of an internal resistance of a current source is infinite. So you use the current source and leave it open circuit. No. Well, you can't build an ideal circuit. It's not possible. You can consider what would happen if you could have an ideal one, but you can't build one. Right? Believe me? You are, okay. That's like all these people who told me perpetual motion. Okay. This may sound a little bit complicated in words, but as long as you apply a methodical approach and label everything carefully, it's relatively simple. Now, we're going to go through an example together, and I really do say that you should be drawing the two circuits separately, properly taking out the relevant source and putting the short circuit in so you can see exactly what you're trying to do. Okay, so follow this example through, and if you get a question like this, you should be able to do it. So what we're going to do is use the superposition theorem to calculate the currents in the circuit and hence find power dissipated in we've got two sources. One positive to the top, which is up in that direction, and we've got V2 of 10 volts, positive terminal up, and we've current in the upward direction. Okay? For currents, I'll tell you now about this node at the top here. At this moment in time, we've got two currents going in, we have to assume that the third current is going down there. Everyone understand that? That circuit is the complete circuit. I could describe that as when we look at it later. Situation where a battery charge would be real complicated. But you can see okay? Doesn't really represent any circuit that I know of. Okay? But it's the simplest circuit I have to demonstrate the superposition theorem. I can't have any simpler than that. Right? So trust me. So first thing we do in the process is we remove the source 2, okay, and replace it with a short circuit, because a short circuit is the resistance of an ideal voltage source. We're taking V2 out of that side and I put a short circuit in. And I made it like that so you can see that something been replaced. Circuit. Now what we can do is add load current arrows as per normal convention for this part of the circuit. So if I go up the top here, which way would I think current is going to flow up here? To the right? Yeah. So we'll put being I. Okay. Where would current flow in the middle leg? Relay. And where would current flow in the artery? That's different to the direction we had on the complete circuit. Put it in. Right. So we label those currents. If we were interested in voltages, we could label those up as well across each of the resistors. But this question hasn't answered. Now, how can I go about calculating the currents F1A, F2, and F3? What, Kirchhoff's? If we want to find F1A by Kirchhoff, we need to know I2A, I3A. One current missing, so that won't work. Is 15 voltage volts of V1 across R1. How can I do that now with the information I've got? The only information I've got at the moment is 1 voltage and all the resistances. Well, the total current from this in this leg, I1A, yeah, that's the one that we can calculate first. But how? Yeah, find the total resistance of that, and that together. How are they connected? Which two are in parallel? So RT here, the total resistance for circuit A is R1 in series with R2 and R3 in parallel. This is like the circuit you've been working with, except the resistors are drawn slightly different way round. But it's, if you look at what you need to do if you're struggling with this, is look at current flow. All the current has to go through R1. It must be a series resistor to that source. But then it splits and goes some through R3 and some through R2. So that resistor is in series with those two in parallel. See that or not? So there's the series bit, there's the parallel bit. So we're calculating that all in one go here. So the value of R1 is 6 ohms, R2, 5 times 30 over 35 equals, sorry, 10.29 ohms. Yep. Now we know the total resistance, what can we calculate? Yeah, because what we've effectively got here now is we've replaced all those 3 resistors with 1. So we've got 15 volts and 1 resistance of 10.29, and I1A, all of that current from that source flows through it. Yeah, so that calculating the total resistances simplification will allow us to find. How do we do that? I is V over R. So V1 divided by RTA is equal to 15 over 10.29 equals 1.46 amps. Yep, and we'll put that, because that's one of the things we're really interested in, 1.46 amps on the diagram. Yeah. So now we have the other. The right way round. How would you do it? Mm-hmm. Idea? from there. We can find that, take it away from V1, we'll have that voltage across both of those resistors, and that'll allow current to VR1 is I time R1 1.46 times 6 ohms by Kirchhoff's voltage law, R2 V1 minus R1 15 take away 8.75 6.25. And we can use that to find I2A 6.25 5 6.5 30. What that is. 1 point something. And I 0.23 208. Add them two together, what do you get? 1.458. How does that compare with 1.46? Yeah. We'll write these currents on this diagram now. So what was I2A? 0.25. And this one, right, what I'm going to do now is jump ahead to the final drawing and write on here I1A I3A 2A in red and put values on. So 0.25, this was 0.28, and this was 1.46. Have I got them right? Yep. So that's the first three currents and the overall diagram. So we've superimposed circuit A currents onto the diagram. What, this one? Yep. You must keep these arrows the same way as they are on your circuit diagram that you've calculated them from. Right? Yeah. We're happy with that. So next part is remove V1 and replace it with a short. So gone back to the original diagram, I've taken out V1 and replaced it with the internal resistance of an ideal voltage source, short circuit. Okay, so now I've got a voltage source 2. Which way is current flowing in the right hand leg? Put it in the top, put it up there. So that's I2B. What about in the middle leg? Down. I3B. And what about in the one leg? Down, or if we put it, got more room, right to left. Yeah, agreed? Now we've got to go through simple maths, or you have, to calculate currents I2B, I3B and I1B. Bearing in mind this time we've got R2 in series with R1 and R1 and R3 in parallel. Yeah? So make sure you pick the right ones, but the process is exactly, we've got one resistor in series with two others in parallel. So your job over the next 10 minutes is to calculate the currents I1B, I2B and I3B. For those watching the video, that'll be on part 3.